In this video titled Electrostatic Part 5, we will be studying about electric flux and Gauss theorem. Before we talk about electric flux, let's understand a term, the area vector. For a given plane surface with area S, see figure A, the area vector is defined as S vector equal to area S, that is magnitude of the area, multiplied by a unit vector n cap normal to the surface. Here this is the direction of the area vector. For a curved surface, the area is divided into a large number of elementary surfaces, very small surfaces, each of area ds, and for each element we draw a normal which gives the direction of the elementary area ds. That is, this ds vector is ds multiplied by the unit vector n cap. So one thing should be remembered here: if you take the elementary area here, it will have a different direction. At this point it will have a different direction. So the unit vector n or each element ds area is in different direction. Coming to electric flux, the flux is denoted by symbol phi e and is taken as the product of the field vector, that is electric field intensity, and the area vector S, provided the field is uniform. So flux is scalar product or dot product of field intensity vector and the area vector. Here we assume that the field is uniform at all points on this surface. N cap is normal, which gives direction of the area vector. If theta is the angle between the electric field intensity and normal to the surface, then flux is given by Es cos theta. However, if the field is non-uniform, then the flux is calculated as surface integral of E dot ds, where ds is any elementary area as a part of the total surface area. That is, flux phi e is integral E dot n cap into ds or E ds cos theta. This definition is valid for non-uniform field, and this definition Es cos theta valid for uniform field. Electric flux, being dot product of electric field intensity and area, is a scalar quantity. Its SI unit is unit of electric field intensity, that is Newton per Coulomb, multiplied by unit of area vector, that is meter square. The physical significance of electric flux is it's a measure of the total number of electric lines of force which pass through this surface and normal to the surface. Dimensionally speaking, the flux phi e is Newton, that is m/t minus 2, multiplied by area, that is L square, over charge, that is ampere into time, current into time. So overall the dimensions come out to be m L cube t minus 3 a minus 1. In the next part of the video we will be relating Coulomb's law with Gauss theorem, that is, we will be deriving Gauss theorem from Coulomb's law and conversely Coulomb's law from Gauss theorem. Coming to Gauss theorem, the Gauss theorem relates the electric flux linked with a closed surface to the electric charges inside the surface. According to the theorem, the surface integral of electric field, which also means the electric flux, linked with a closed surface is 1 over epsilon naught times the total charge inside the surface. Example, if you have a surface here, closed surface S, and there are a number of charges inside the surface, then the flux, electric flux phi E is integral E dot ds over closed surface S is Q over epsilon naught, where Q is sigma Qi, that is Q1 plus Q2 plus Q3 and so on, algebraic sum of the charges inside the surface. Remember, the charges outside the surface will not contribute to the surface integral. The contribution to flux only comes from charges enclosed inside the surface. The theorem can be verified in simple case using Coulomb's law. For the purpose, let's consider a point charge Q at O and take a spherical surface of radius r around this point charge. By Coulomb's law, if you have a charge at O, the electric field intensity at a point P on this spherical surface is given by 1 over 4 pi epsilon naught Q over r square, r cap, where r cap gives the direction of the electric field. Taking this charge to be positive, the field will be directed radially outwards. If we take an elementary area, there is small area ds around P, then the flux through this elementary area will be given by d phi E, that is E dot ds. Now the field vector and the normal, that is the area vector, they are in same direction. So the angle between the two happens to be 0 degree. So d phi E can be written as 1 over 4 pi epsilon naught Q over r square r cap dot ds, which implies d phi E equal to 1 over 4 pi epsilon naught Q over r square into ds, because cos 0 is 1. To get the total flux linked with the entire surface, we need to integrate this d phi E. That is, phi E is equal to integral of d phi E over the entire surface. So Q over 4 pi epsilon naught r square, this is value of E, into integral of the elementary surface ds. The total, this gives you, integral gives you the total area of the sphere, which is 4 pi r square, and simplification leads you to Q over epsilon naught. That is, the flux phi E is 1 over epsilon naught multiplied by the charge Q inside the surface. Let us now derive Coulomb's law from Gauss theorem. For the purpose, we consider this diagram once again, where we have a point charge Q at the center O of a sphere of radius r. This sphere we take as the Gaussian surface. Gaussian surface is any convenient surface, however it should be a closed surface, and to such a surface we can apply Gauss theorem. If we consider an elementary area ds at P, here elementary area ds at P, the electric field is directed radially outwards, and so is the normal to the surface. That is, area vector and the field, electric field intensity, they have same direction. So angle between the area vector and the field will be 0 degree. So the flux linked with this elementary surface of area ds, if we denote it by d phi E, it will be E dot ds. Therefore, if you want to find out the flux with the linked with the entire Gaussian surface, we can get it by integration of E dot ds. Now integral of E dot ds can be written as E into ds, because theta is 0 degree as stated earlier. That is, the area vector and the electric field intensity, they are in same direction, and the angle happens to be 0. Since the magnitude of the field, because of spherical symmetry, remains constant everywhere at every point, so this E can be taken out of the integral, and you have to just integrate ds, which will give you the area of the sphere, that is 4 pi r square. And if we apply Gauss theorem, the flux phi E is given by 1 over epsilon naught into the charge enclosed in the surface, which is Q. Comparing these equations, you will get the magnitude of the field as 1 over 4 pi epsilon naught U over R square. If we keep a charge Q dash here, the force on this charge Q dash due to Q will be given by a definition of the field, that is force equal to Q dash into E, which leads you to this expression 1 over 4 pi epsilon naught Q dash over R square. This is, as you know, Coulomb's law, which we can deduce from Gauss theorem. Applications of Gauss theorem we'll see in the next video, that is electrostatics part 6.